Alright, so we are back with the intermediate axis theorem. And for those of you who do not remember what the intermediate axis theorem is, it says that with an object, when it is rotated about its intermediate most inertial axis, it does some weird stuff. Are you ready? I'll demonstrate for you. Do you see that little turn?
Yeah, I did.
This is what our lab is on, and we already did a lab on this, but we wanted to explore some, as you recall, some different values.
So yeah, we had some theories on what ratios would give the least stable flip. So the ratio between length and width, we thought that it'd be between 1 and 50, the most stable.
Alright, and then our other theory was that the least stable flip would occur when the ratio was an average of the length and height. And here's like a little graph to show you what we kind of visualize that would look like. A nice little curve, H plus L over 2 right at the peak.
And then and then we thought it would be when the inertia is the average of the other two moments of inertia.
Here.
And then we solve for width.
Yeah, I'll show you that math right here. So we took these equations we got online for inertia in a rectangular prism. It's just 1/12 times the mass. This is about the y-axis. You got a little diagram right there. Width squared plus length squared. And so we did that, and we said the intermediate axis, the inertia of the intermediate axis is equal to the inertia of x and y axis divided by 2. And then we solved for the width because we kept height and length constant.
I can't read your handwriting.
Here, come back. This is all that really matters. These two things. That's the initial. That's the conclusion. You good? Yeah.
Can you make that face? Wait, the one that's in your background? Yeah. Oh, there you go. Okay.
All right.
The equipment we used a wood. We used pieces of wood, and then a handsaw and safety goggles. I sat on the wood while he cut it, so you might need something to
Yeah, actually,
hold on the wood.
it was just really loud saws. It was kind of dangerous.
Really loud.
We did some dangerous stuff. It was provided by Dr. Schuster.
The handsaw?
Yeah.
Yeah.
We'd call it a power saw, probably, if it was not.
Well, I held it with my hands.
It's a good point. A lot of things could be hand things then.
We needed a yardstick to measure the wood, pencil, and iPhone with slow motion feature. And then
All right. So we cut 8 pieces of the wood of this. We cut 8 pieces of wood of the same height and length with different widths. And we flipped each board about its intermediate axis 3 times, and then everything was recorded in slow motion so that we could analyze, oh, this is flip, this is spin in slow motion, which makes it a lot easier. And we looked at the flip to spin ratio. It's kind of confusing, but we define, I think, this as a flip and this as a spin. So as it was going around the air, it was doing something like that. It's kind of hard to mimic. We looked at that, say, all right, it flips this many times, it spins this 10 many times. And we use that ratio of, I think, spin to flip to determine sensitivity. And here's an example trial.
Full screen.
Full screen.
Oh, that's not full screen.
You didn't think about 2-minute long ways? Is that your house, Jack?
I'm not telling you.
Here's our data. And I guess I'll just show you the graph. Yeah, so for the length to width theory,
We kind of came out with nothing. Spin to flip versus length to width. We didn't find any. It doesn't really look like there's a huge trend.
There's a formatting issue. I can't see the bottom of the graph.
I can try to drag it up.
I'm sorry. I think it's
Like it's not in full screen presentation mode anymore. Maybe you can go, I don't know, refresh it or something. I'd hate for you to have my taskbar on the whole presentation.
Click there.
Yeah.
So, and then this is just graphed width, instability, and as the width approached this value, the instability peaked, and so
This was nice. So it was. Yeah. So we found that it wasn't necessarily the ratio, but the width.
and this value is between height and length.
And so here is let's see, which one's which. So this is the average instability. So the 0.3125. This is when the width was the width value for when the intermediate axis was the average of the two other inertias, and that was 0.3125. And then 0.505 average instability, that was when the width was an average of the length and height. And so from that, we can conclude that our data supports the theory that when the width is an average of the length and the height, then the wood is least stable. Sources in there.
Well, flip inconsistency because not every flip is the same, so some flips might make it spin. And wind could vary on different trends. And imperfections in the wood, measuring surfaces, density. And then it was kind of hard to analyze the flips, so that could contribute.
And from this experiment, we can conclude that the instability peaked at a value between height and, when the width was at a value between the height and length, specifically when it was the average of the height and length. This does not support the first hypothesis that when with the whole ratio idea, that there's this ratio of the length and widths that result in the max instability. It was really the value of width in relation to the length and to the value of width in relation to the length and height. And at peak instability, the value of width was closer to the average of height and length than the value of the inertial value we got with the averages of inertias in solving for width, which was kind of weird because you'd think that using equations that were actually found to be true, you would get a better result, but instead we had this ballpark idea. I was just like, maybe it's this, and it turned out to be averages of length and height. I kind of talking about this. In the future, yeah, you go ahead.
Yeah, in the future we would use a wider array of widths and do more trials for each width. And then it'd be better to do it indoors to eliminate wind. You could do it in a vacuum.
All right, that's it. Thank you.
Got a question?
I have some wood if anyone wants it.
Oh,
This is our, the one the ratio was 1. This was when, I'm trying to think.
I think,
If you were to ask me this a month ago, I would have known. One of these is when the length and width are averaged, and one is when the intermediate inertia is the average.
Can you toss them right now and see which one's less stable?
Yeah.
Is that the way to figure out the ratio rather than measuring
I'm
them?
gonna drop it.
Alright, ready? Here's one of them. Here's another one.
Ooh, that did not look very stable.
No, here's the one.
Pretty stable.
Yeah, so I think it went most stable, intermediate, least stable, least stable. There you go.
Moments of inertia.
Here.
And then we solve for width.
Yeah, I'll show you that map right here. So we took these equations we got online for inertia in a rectangular prism. It's just 1/12 times the mass. This is about the y-axis. You got a little diagram right there. Geo was an average of the length and height. And here's like a little graph to show you what we kind of visualize that would look like. A nice little curve. H plus L over 2 right at the peak.
And then, yeah, and then we thought it would be when the inertia is the average of the other two.
Straight for you. Do you see that little turn?
Yeah, I did.
This is what our lab is on. And we already did a lab on this, but we wanted to explore some, as you recall, some different values.
So yeah, we had some theories on what ratios would give the least stable flip. So the ratio between length and width, we thought that it'd be between 1 and 50, the most stable.
Alright, and then our other theory was that the least stable flip would occur when the ratio. Alright, so we are back with the intermediate axis theorem. And for those of you who do not remember what the intermediate axis theorem is, it says that with an object, when it is rotated about its intermediate most inertial axis, it does some weird stuff. Are you ready? I'll demonstrate.